Hello everyone. In this video we are going to talk about interpolation and curve fitting. So curve fitting is when you have some data from some experiments and you don't really have the underlying function, you know what it might be, and so you're trying to fit that function to this data and find the unknown parameters of that function. So let's say here I have some data x1 and y of curve fitting, and x is a bunch of data between -5 to 5, 50 equally spaced, and then y is a sine function with the frequency of 3 radians per second and amplitude of 2, and I add some random data to it so it's not perfectly on a sine wave. Then I define the shape of the underlying function that I think I should fit to this x1, yc pairs. And I say, I think the shape is a sine of b times x, which is exactly, if you look, the shape of this function here, right? Because I have some prior knowledge, or that is when you have a very good knowledge. And then you use the curve fit method from the optimize, and optimize is a sub-library from the Scipy libraries or modules. And this curve fit method, it is going to fit your test function that you think it is to the pairs of x and y, and you give it some initial guess for the parameters that you have. So here I have two parameters in it. So my numbers are going to be guess 1.5 for A and 2.5 for B, but you see the actual values are 2 and 3, not 1.5 and 2.5. And then this is going to get you the values of the parameters that it converts to. And here I'm going to show you in a scatter plot the original data that you got from the experiment, as well as passing the X data to the function that I think it is going to fit with the parameters that I found from what? From my optimizer. So I'm going to pass these parameters and my data points to the test function that I think it is. That is going to give me some y data. I'm going to plot that x and y data, which I think that's the curve fit data, and plot it over my scattered experimental data and see whether there is a good fit or not. Okay. In the next part, I do the exact same thing. This time, instead of the sine function, my underlying function is a linear function. And again, the a and b are 2 and 3 here. And again, I have added some random numbers, so my data are not perfectly on a line, right? You see my normal data are coming from a normal distribution with average of 0 and standard deviation of 0.75 and 50 data points. This 50 exactly is the same as what? The size of x data, or the size of this vector here, 2 plus 3x. They have to be the same, otherwise you cannot add them together. And then, again, the function I think it is a plus bx, where a and b are two parameters to be estimated. Again, I pass my test function, my x data of experiment, and the y from the experiment, plus some guesses for initial parameters to it. It gives me the final parameters. And again, I do a scatter plot of experiment. On the top of that, the plot of the curve that is fitted to it, and see if I did a good fit or not here. And to do that, you have to bring in the optimize, as I said, from what? From Scipy. Otherwise, you cannot do this portion here. So let's go ahead and run the first part of the code, which is on curve fitting here. So here we go. So as you see, the blues are the data from my experiment, and the red is the curve I think it should be. And you see the fit is not really bad, and the parameters I have estimated are 2.06 and 2.98. The actual values are 2 and 3. You see these are very good guesses of those. And the reason for that is the amount of this the values that I added to my data is not crazy large. There are some uh, points that the curve that is fitted is a little bit off from the experimental data, but overall it does a very good generalization. Okay, and the bigger I choose this standard deviation and the bigger this random part is compared to the actual signal, or what we call the signal the smaller the signal to noise ratio, then you clearly will have further off parameters from the actual values, and your curve fitting is not going to be as good, but that's how it is. So this is your sine function, and then this is your linear function here, which you can see these are my linear data here. They are not too bad. They are not too off from the line. So the curve fitting is a very good fit. And you see here I have 1.91 and 2.96 for the estimates of 2 and 3, which is again not too bad. Okay, so you get this x and y data from any experiment. You define a test function which you think should be on the underlying function, and you call this optimized curve fit from Scipy to get you the parameters of your unknown function, right? And this is what we call a curve fitting, right? So this is the curve fitting. And then we have interpolation. Interpolation is when you have data and then you want to basically find the value in between the data points. So you got some data from some experiment, some x and y, and you want to basically not only fit a function between the data points, but you want to also use that function to find the value of y for any x where x is between the test points, right? So let me first show you that, and then I explain the code for you. So let's say here I did some experiment and my data are these blue points. Okay, these are the data that I got. Now, if I want to know the value of y at this point here, which is between these two experimental points, what is the value of y? Because forget about these two curves that I added. I just have a bunch of points. That's all I have. Now, if I say, hey, if I did this experiment, let's say this is x of 2 and this is x of 3. If I used x of 2.5 or 2.3, what would have been the y value? So if I want to read y in between the x's, I need to what? I need to assume the type of function that describes the variation of y versus x in general between two consecutive points. And that is the type of function that you consider here. One of them is a line, so you can assume that it is only going to change linearly between two data points, or you might say, no, it is going to change like a cubic function between two consecutive data points, okay? And each one of them, of course, gives you some different values, especially when the variation in the trend of the function is sudden, okay? And it changes the trend. You see that your linear function and cubic or quadratic would be quite a bit different. Linear is good typically when the experimental points are very close to each other and I have a bunch of samples. Otherwise, other functions might give you a little bit better estimates in general, but if we don't have the underlying function, we don't really know which one is better than the other. You have to have the actual function, which in most of the cases you don't. So you either do linear or cubic or any other kind of function that you assume, and then if I know it's a linear function between 2 and 3, then at 2.5, it's kind of the average of the two y's. Or if it's at 2.3, it's going to be 30% value of the 2 and 70% of the value at, or basically the other way around, 70% at 2 and 30% at 3, right? So it's going to get a bigger weight from the data that is closer to it. And this is the idea of interpolation that you all know. So here I have generated X and Y. X is just a bunch of data between 0 and 10, 11 data points, and equally spaced. And my Y is cosine of basically X squared over 9, okay, which is kind of a harmonic function with increasing frequency. And then here I do two things. One, I pass my X and Y to an interpolation function called interp1d, and this is for 1D interpolation. One time I don't pass it any type of assumption. The other time I say kind cubic. When I don't provide any option by default, it means it's going to be a line. So this is going to be, this f is going to be f linear. This f2 is going to be what? A cubic interpolation. So it generates a linear and a cubic interpolation in between the points, and between each 2 points there is a line. Between the next 2 points is a different line, and then a cubic polynomial between these 2 points, between next 2 points, again another cubic polynomial, and these cubic polynomials are smooth. So this is going to be like the S-spline basically idea. Now I'm going to generate a lot more data points, more than the original data. Why? Because I want to go in between the test points. So I generate a lot more data points and then pass this test points, which are a lot more than original one, to both the linear interpolator and to the cubic interpolator. And on the top of my original data, I'm going to also show you the linear interpolator curve and the cubic interpolator curve with the legend so you can see. If I want to use the red lines, these are the linear interpolators between 2 points, and this dash green is what? Cubic one, right? So if I want now the value at 2.5, all I need to do is to pass 2.5 to f and to f2 and get the values for them and see how much they are, right? So all I need is something as simple as saying basically print linear interp at x equal 2.5 is, and cubic interp at x equal 2.5 is, and then format, and then here it is going to be f at 2.5 and f2 at 2.5, and that should give me both of the values. So let me run that for you. Seems like I did something. There is something missing, probably an extra parentheses. And go ahead. There we go. So you see the value of the linear function is what? 0.72. The other one is 0.76, and you can kind of see that, right? Here at 2.5, we are here, and you see that the cubic curve is a little bit what? Above the line, and they are about 0.7 something. Okay, so you clearly see the interpolation using a line and a cubic function. And you can use any function that you want, but typically line and cubic are the most common used functions for what? For 1D interpolations. So this is how you do curve fitting. This is how you do 1D interpolation. And for that, for the curve fitting, again, you need optimize from Scipy. For the interpolation, you need to bring whatever interpolator you use. In this case, interp1d. You have to bring it from Scipy under interpolate submodule. So from Scipy interpolate, bring in what? Interp1d. There is interp2d and all sorts of things that you can do 2D interpolation and so on. But I guess once you know how to do a 1D, then 2D is just changing the syntax. So it shouldn't be that hard for you. So hopefully this video was useful to you. I will see you in my next lecture. Thank you.